Okay, let's start. Okay, so today we will learn about this intermolecular bonding. Now, intermolecular bonding, okay, is a very important bonding because last time, okay, when we learned about this bonding, okay, when we learned about intramolecular bonding, okay, which is the other one, okay, the intra is going to be the bonding, okay, within the molecule. So we have, okay, covalent bonding, we have ionic bonding. Okay, these are the two main ones. Okay, a special type of covalent is going to be coordinate dative bonding. And we also learned about, okay, one kind of intermolecular bonding, but I'll just put it separately over here, which is going to be the metallic bonding. Okay, it's the bonding between metal cation and the C of delocalized electron. Okay, so this one we have learned before. Okay, but okay, very important. If I actually take a look at the intermolecular bonding, do remember, okay, intermolecular bonding generally they are weaker bonding. Okay, they are weak um, compared to your ionic bonding, compared to your covalent bonding. Okay, they are weaker. Okay, they're definitely weaker. It means that you do not need a very high amount of energy to break the intermolecular bonding. Okay, the strongest, okay, bonding is going to be generally ionic bonding, okay, followed by covalent bonding. And then you have intermolecular bondings. What are those intermolecular bondings? Today we will learn all these three. Okay, there are three. One is called permanent dipole-dipole. Second is going to be hydrogen bonding. And the third one is going to be VDW, that stands for Van der Waals bonding, or Van der Waals forces of attraction. Okay, so we have total of 3 intermolecular bonding. But before I go to this intermolecular bonding, I just want to actually introduce this concept in a different way. Let's actually try whether you can understand this concept better. Okay, if you have water molecules, okay, this is going to be H, O, H, and then we know that, okay, they have 2 lone pair. Okay, so let's actually see whether you guys remember this. Josh, tell me what is the shape of water?
It's bent.
Okay, it's bent. Other names, Kenneth? It's also known as non-linear.
I don't know. Yeah, no.
One more, Kenneth? There are 3 names that you can use in our syllabus. Okay, bent, non-linear, or V-shape. Okay, but Kenneth, let's actually try to answer the bond angle. What is the bond angle of this water?
I forgot. Is it 104.5?
Yes. Okay, it's 104.5. Okay, so do remember this. 109.5 is for tetrahedral, which is CH4. 107 is going to be for ammonia. Okay, that is, this is for 4 bonding pair. Okay, this one is going to be 3 bonding pair and 1 lone pair. And if you have 104.5, that's going to be 2 bonding pair and 2 lone pair. So you remember these 3. Okay. So now, okay, I'm not interested with that. Okay, I'm interested with water now. Okay. Now, if I have water molecule, okay, if I have water molecules, and I'm going to boil. Okay, I'm going to boil water. So it means in order to boil water, the boiling point. Okay, Nevan, can you tell me the boiling point of water?
100.
Okay, 100 degrees Celsius. At 100 degrees Celsius, if I want to write it in form of chemical equation, H2O, okay, in form of liquid is changing into what? Ashley?
Yes, sir.
H2O in form of liquid is changing into what when you boil?
When you boil gas.
Okay, so you are getting H2O in form of gas. Now, what is this type of bonding? Justin? O and H. What is that?
Covalent.
Okay, good. So it's covalent bonding. Now, I want to actually just want to be very sure about this. When you boil water, are you breaking the covalent bond?
No.
Okay, you are not breaking the covalent bond. So if I actually have water, okay, if I just generally put water as like this, and then I have water over here, okay, what is exactly that we are breaking? Okay, we are actually breaking the forces of attraction that holds one molecule of water with another molecule of water. Okay, that force of attraction is the one that we are going to learn today, which is going to be what we call as intermolecular forces of attraction. Okay, intermolecular forces. Now, do remember, okay, if you want to break the bond, okay, of course you need to break the weakest bond. Okay, that's the reason why this bond is being broken rather than the covalent bond. Okay, that's why you don't actually get water when you heat up. You don't actually get hydrogen and oxygen. Okay, this is not going to happen. Okay, because we are not actually breaking the covalent bonds over there. Okay, what we are breaking over here is we just breaking the weak intermolecular forces with one molecule to another molecule. So do remember, whenever we have molecules, when we say boiling point, when you are trying to boil something, we are trying to break the intermolecular bonding. For another example, if I give you one more example, ethanol. Okay, ethanol, the boiling point of ethanol is going to be 70 degrees Celsius. Okay, that's the boiling point of ethanol. Now, when I want to boil ethanol, okay, into gas, what type of forces of attraction that I'm breaking? I'm breaking only the forces that holds ethanol with another ethanol. Okay, and they are going to be connected. Okay, so these are the forces that I'm going to actually break. I'm not going to actually break the bonds. Okay, if ethanol, this is the structure of ethanol. I am not going to break any kind of forces that involves O and H, because one of the common misconception that students think when it comes to ethanol, when you boil ethanol, they think that, oh, this one is hydrogen bonding. Later, I'll teach you about hydrogen bonding. Okay, they think that this is going to be hydrogen bonding, H and OH. So this bond must be broken. It's not true. Okay, it's not true. I will go into that later. Okay, so if I actually put it in form of, let's say, what is intermolecular bonding? Okay, it's more towards like this. If imagine, okay, you have a couple. Okay, you have a couple, and then, okay, they are deeply in love with each other. Okay, they are deeply in love with each other. Okay, and then you have, okay, another couple, they are friends. Okay, they are friends, and they also deeply in love with each other. Okay, and both of these couples, they are friends. Okay, so this is friend bonding, friend bond, and this one is couple bond, couple bond. So just remember, okay, the couple bond or the love within themselves is much more stronger. So if let's say there is any issue, you want to separate them or you want to actually do something, okay, most likely the friendship bond is going to be broken. Okay, so we are looking into the friend bond over here. Okay, the intermolecular bonding is the friend bond. Okay, so we have different types of bonding. Okay, so I hope it's clear. Okay, but now let's actually look at how do we determine this kind of bonding. Okay, Now, this kind of bonding we can determine based on the concept of polarity. Okay, first we need to revisit, okay, the concept of polarity. You need to know which molecule is polar, which molecule is non-polar first. Okay, so if I have CH3Cl, okay, how do we determine whether this molecule is polar or non-polar? Okay, so this is going to be carbon. So carbon is bonded to 3H. Okay, so H, so you have H, you have another H, and then there is one Cl. Now, do remember the concept of electronegativity. Okay, can someone tell me the meaning of the concept of electronegativity? Maybe Ella, can you actually tell me the concept of electronegativity?
The ability of an atom with its covalent bonded to another atom to attract the pair of electrons to itself.
Okay, good. Okay, it's the ability of atom to attract covalently bonded electron pair, covalently bonded electron pair to itself. Okay, I think that is actually much more shorter, to itself. Okay, so that is going to be the electronegativity. And if you actually revisit about the periodic table, I have already mentioned this in class. Okay, if you have, for example, when we are talking about, okay, going across the periodic table, okay, so we can say that the electronegativity, okay, electronegativity will increase. Okay, why? Increase in proton number. Okay, shielding effect remains constant. Okay, so nuclear charge is going to be more. Okay, but when you go down the periodic table, okay, even though the proton number is increased, but the distance and the shielding effect will outweigh the increase in proton number. Therefore, your electronegativity is going to go down. Okay, so we can use this to predict. But whatever it is, okay, do remember carbon and hydrogen. Okay, hydrogen, okay, if you actually put it in form of, let's say, in form of chemistry mark, okay, let's say we do a test, okay, the lowest supposed to be 0%, the highest is 100%. Okay, imagine that hydrogen is towards the low performing, so hydrogen is going to be the one that actually getting the lowest mark in chemistry. Okay, and imagine the highest mark. Okay, the highest mark I will tell you now itself, I think easier for later lesson. Okay, so this one, the highest performer, okay, will be, okay, chlorine. Okay, imagine chlorine getting 98%. Okay, sorry, wait, it's fluorine. Okay, it's fluorine. Then oxygen and nitrogen. Just imagine fluorine is getting 98%, this one getting 97%, this one getting 96%. Okay, imagine NOF, nitrogen and oxygen, are the top performers of the chemistry test. The lowest performers are hydrogen, and just take into note, carbon also almost the lowest, okay, which is similar to hydrogen. Imagine hydrogen getting 1%, okay, and then carbon is getting 2%. Okay, therefore, they have found, okay, because they are closer, they have found that carbon and hydrogen, they say that electronegativity is almost the same. Okay, they have said that electronegativity is the same because of this reason. Okay, so like for example, if I have carbon and hydrogen, I can say that since they have the same electronegativity, the electron stays in the middle. The electron stays in the middle. The electron stays in the middle. But comparing carbon and Cl, okay, Cl, okay, is going to be, just remember carbon is the weakest, okay, and then you have Cl somewhere in group 17, which is going to be more electronegative. Okay, what happens? They will pull the electron towards the Cl, and that makes, okay, that makes this entire thing is going to be delta positive. This is going to be delta negative. Okay, so what happens if I actually put it in form of, let's say, a molecule? It means the top part is going to be delta negative, the bottom part is going to be delta positive. So since you have this, so we say a dipole is created. Okay, a dipole is created. What is dipole? Positive and negative. Okay, a dipole is created. The moment the molecule has dipole, we say that molecule is polar molecule. Therefore, I can say that, okay, this molecule is polar. Okay, as simple as that. Now, sometimes, okay, we do have some examples like this. Carbon double bond with O. This is carbon dioxide. Now, when you look at carbon, yeah, you know carbon is the lowest. Of course, oxygen is going to be group 16, so they are somewhere here. Okay, of course, they can actually attract the electron towards itself. Okay, the oxygen. Supposed to be this one, supposed to be delta positive, supposed to be delta negative, supposed to be delta positive, supposed to be delta negative. But what happens is, imagine, okay, you have a lady over here, okay, and then one guy is trying to pull her hand, okay, is trying to pull her hand, okay, towards this side, okay, and then the same guy is trying to pull this girl's hand towards this side. Okay, what happens? Okay, imagine that the hand don't break. Okay, she will be still staying in the middle. Okay, she will be still staying in the middle. It means I can say that the force exerted by this guy and the force exerted by this guy is going to be cancelled out with each other. Okay, so in chemistry, if we try to relate over here, it's going to be, we call that force, okay, the one that is going over there, because it's dipole. Okay, we call that force as dipole moment. Okay, it's called dipole moment. So of course, this one is also called dipole moment. So what we say in a molecule that is going to be symmetrical, if you're pulling in equal direction, opposite direction, okay, we say that the dipole moment is cancelled out. Okay, dipole moments are being cancelled out. So when the dipole moment are being cancelled out, what happens to the net dipole? Okay, the net dipole becomes 0. Okay, that means I can safely say that carbon dioxide is going to be non-polar. Okay, why? There is no dipole. Okay, there's no dipole, but it doesn't apply for all. Okay, I'll show you another one, two examples. One is going to be BF3. Okay, another one I'll show you related to PCl3. Okay. BF3, boron is going to be from group 13. It means that they have 3 valence electrons. So you have this structure, and then this is going to be a trigonal planar with a bond angle of 120. But phosphorus, on the other hand, okay, they do not have the same shape. Because phosphorus, if you look at your periodic table, they have, okay, 5 valence electrons. It's group 15. So 3 of the electrons are being used for the bonding with the Cl, and the remaining 2 will exist in form of lone pair of electrons, something similar to ammonia. So the shape is going to be pyramidal, and if you remember, I hope you remember, the bond angle is 107 degrees. Now what happens over here is, okay, there is going to be a dipole. It means there is going to be, we can say the bond is polar. Okay, why the bond is polar? It's a different atom, different electronegativity, boron and F. If you look at your periodic table, boron is somewhere here, F is somewhere here. Of course, this one more electronegativity. So it means the electron will go here. The electron will go here. The electron will go here. Okay. So what happens? The bond is polar. But imagine you have, okay, you get the, I hope you get the idea. Imagine 3 guys trying to pull a girl okay, at 3 different directions, and then the girl refused to follow any of them. They stay in the middle, okay, because they are being pulled at symmetrical angle, yeah, so they do not move anywhere. So we say that this molecule is going to be non-polar because same explanation, the dipole moment is being cancelled out with each other. But things are going to be different the moment you have lone pair of electron, because the moment you have lone pair of electron, they are not going to be symmetrical anymore. Okay, the presence of lone pair is going to make a lot of difference. Okay, if you compare P and Cl, okay, P and Cl, again, I told you Cl is the top performer. If you no, Cl is not top performer, but if you look at the periodic table, okay, phosphorus is going to be group 15, Cl is going to be group 17. So of course, the one that is more towards the right will be more electronegative. Okay, so the electron is supposed to move towards Cl. Okay, and imagine there are 3 people being they are pulling the electrons, and they are not going to be symmetrical. Okay, and then there's also electrons over here. Okay, so what happens over here, since it's not symmetrical, and then they have lone pair. Okay, the presence of lone pair actually makes the molecule non-symmetrical. So it means that most likely the electrons will follow the Cl. It means if I put it over here, PCl3, I know that this part will be most likely delta negative compared to this part. Okay, so what happens over here is, okay, there is a dipole. The moment there is dipole, we say that this molecule is polar. So we actually determine polarity using this. Okay, polarity using this. Now, why we are revisiting this again? Okay, if you ask me. Okay, of course, there's a reason for it. Imagine, okay, now I have a polar molecule. A polar molecule, one example, okay, let's say we take PCl3. Just now we said that PCl3 is a polar molecule. It means that PCl3, there is a dipole. There's a delta negative, there's a delta positive. Okay. Imagine you have another PCl3. There's a delta positive, there's a delta negative, each of them. Yeah. Now what happens, okay, there is a force of intermolecular forces of attraction will exist between negative and positive because opposite charges attract. Okay, opposite charges attract. So these particular forces of attraction, there is a name for it. Okay, there's a name for it. This is dipole, and this is dipole. This positive and negative will be always be there. Okay, no change about it. So it's a permanent. Okay, it's a permanent. Therefore, this particular bonding, okay, we call it as permanent dipole bonding. So this permanent dipole bonding exists for polar molecules. Okay, they exist for polar molecules. So it's always permanent. Since it's permanent, okay, do remember among all the intermolecular forces is considered to be kind of a very strong bonding. Okay, I give you another example. Okay, if you have HCl, I think very simple example, HCl. We know this is delta negative, this is delta positive. So if you have another HCl, okay, delta positive, delta negative, the bonding between these two is going to be the permanent dipole bonding. Okay. Now, apart from HCl, I can give you some other examples. HF. Similar, delta negative, delta positive, delta negative, delta positive. So they supposed to have some kind of a permanent dipole bonding also. Okay, just wait for a while. Yeah. So this one, they will have some kind of permanent dipole bonding as well. One, they are polar. Okay, of course, then positive and negative is permanent dipole bonding. I'll give you another one more example. This is delta negative, delta positive, delta positive, delta positive, delta negative, delta positive, delta positive, delta positive. Okay. The bonding between this hydrogen and this negative is also, we can say, permanent dipole-dipole bonding. Okay. I'll give you another one more example. Delta negative, delta negative, delta positive, delta positive. The bond between this and this, delta negative and delta positive, that is also going to be known as permanent dipole-dipole. Okay, basically the idea is any polar molecules, delta negative and delta positive from the opposite, they can actually form a permanent dipole-dipole bonding. But yeah, let's come back to this. Now, imagine just now I told you the lowest performer is hydrogen. Okay, lowest performer is hydrogen. The top performer is FON. Any kind of bonding that involves the lowest and the highest must be very, very strong. Why? This is very, very much electronegative. This is very, very much electropositive. Of course, the bonding between them must be very, very strong. Okay, or very, very, very strong compared to the other type of permanent dipole-dipole. Now, that kind of bonding, okay, I think we cannot just simply ignore. I think we need to actually give them a special name, okay. The special name that we give to them, okay, it's still permanent dipole-dipole bonding, but the special name that we give to them is going to be hydrogen bonding. Done, done. Hydrogen bonding is going to be a special type of bonding, permanent dipole-dipole, but it involves hydrogen, the least electronegative and the most electronegative. And I have actually saved the time to draw some diagrams over here for you. Okay, what I've done over here is, if you look over here, this is hydrogen and Cl. I told you H with NOF. Is there any hydrogen bonding over here? No, it's only permanent dipole-dipole bonding. But if you look at HF, it's hydrogen with F. Hydrogen with F. So this permanent dipole-dipole bonding is hydrogen bonding. This is going to be nitrogen with hydrogen. Hydrogen with nitrogen. This is hydrogen bonding. This is going to be hydrogen with oxygen. Hydrogen with oxygen. This is also hydrogen bonding. Okay. So if you look over there, hydrogen bonding is the bonding, a very special type of bonding, a very strong bonding. It means this will contribute to higher boiling point, okay, compared to the other permanent dipole-dipole, okay, because it's very special, because it involves the least electronegative atom, which is hydrogen, with the most electronegative elements in your periodic table, which is going to be nitrogen, oxygen, and fluorine, NOF. Okay, other than that, they are not hydrogen bonding. Okay, so one of the common mistakes that students actually take, okay, or make, is going to be related to just now I draw related to alcohol. See whether I can look at that example. Okay, I don't know where I draw it, but I can draw it again. Okay. Another type of molecule that can actually give you hydrogen bonding is alcohol. Okay, I'll show you. This is going to be alcohol. Okay, alcohol. Okay, is it polar molecule or non-polar molecule? To answer that, very easy. Okay, oxygen is more electronegative than hydrogen. They will actually attract the electron to itself. The moment they attract the electron to itself, that's already delta negative. This is already delta positive. So of course, alcohol is polar. Okay. Do remember this one additional knowledge here. Polar dissolves in polar. It means, okay, it means water is a polar molecule. Okay. Any polar molecule, they supposed to dissolve in polar molecule. That's the reason if I ask you, can alcohol dissolve in water? Okay, the answer is definitely yes. Okay, because alcohol is polar, water is polar, so polar dissolve in polar. Okay, so you can actually memorize this, but it's not important now. Let's actually come back to our original intention of doing this. Okay, so this one you have this, so O and H, delta negative, delta positive. What happens is if you have here positive and negative, this is going to be the bonding between hydrogen and oxygen. Okay, so this one we call it hydrogen bonding. So alcohol itself also, okay, can exhibit hydrogen bonding. So I have actually given you 4 examples of hydrogen bonding. Okay, I think it's good enough. Okay, good enough. Okay, because it will help you to determine which one has hydrogen bonding. One is going to be ammonia. Second will be NOF. You just remember NOF. So ammonia. Oxygen, involving oxygen is water. Involving F is going to be HF. Okay, one more is alcohol. So I'll put it ROH. Okay, so alcohol. So total 4 molecules that can exhibit hydrogen bonding. Okay, total 4. Okay, so that is going to be about permanent dipole-dipole bonding. Okay, and also hydrogen bonding. Is there any question up to here? Okay, no. So we continue. Then how about, okay, now we spoke about polar molecules and polar molecules. How about non-polar molecules and non-polar molecules? Now, the last one is left with van der Waals forces of attraction. Now, van der Waals forces of attraction, the common misconception is students, they tend to think van der Waals is only for non-polar and non-polar. Okay, it's wrong. Van der Waals forces of attraction is for both polar and non-polar. Okay, so it exists in both polar and non-polar, but it is the weakest among all the 3. It means you have hydrogen bonding, permanent dipole-dipole, and van der Waals. Now, van der Waals is the weakest. Okay, followed by this is VDW. Okay, the strongest is hydrogen bonding, and then the second is going to be permanent. I put D and D, dipole-dipole. Okay, permanent dipole-dipole. So you see, this is weakest. Okay, now imagine a molecule has permanent dipole-dipole and van der Waals forces, a polar molecule. Imagine, yeah. Okay, for example, imagine that you are having HCl. I know HCl has permanent dipole-dipole. Okay, because it's polar. And I also know, I just told you that they also have van der Waals forces. But since the permanent dipole-dipole will have, let's say, a higher or stronger attraction, the dominant intermolecular forces of attraction is, okay, permanent dipole-dipole. Actually, you can wait. Okay, no need to eat now. Okay, now, so here, okay, when you look at, okay, HCl, okay, when you look at HCl, we are talking about, okay, permanent dipole-dipole. Even though there is van der Waals forces of attraction, the dominant or the most prominent forces will be the one that is stronger. So we refer to that. So what is van der Waals forces of attraction? It's very simple concept. Imagine you have any kind of a molecule. Let's say we take Cl2, because Cl2 is not non-polar, easier to actually show. Okay, imagine you have Cl2 and another molecule of Cl2. And do remember, electrons, they are like, they will keep on moving around. Okay, they keep on moving around, and you actually take a camera. Okay, you take your, I think nowadays we don't use camera anymore. We just take the phone camera. Okay, you take your phone camera, you take picture. Imagine your phone camera is so advanced until you can see all the electrons. Okay, at that moment, okay, there will be, because the electron, they keep on moving. What happened is at one particular moment, the electron might be more towards here and then less towards here. At that moment, okay, at that moment. So what happens, okay, automatically this one will be negatively charged. Automatically this one is going to be positively charged, okay. And at the same moment, okay, at the same moment, imagine I bring the Cl2 over here, easier for me to show. At the same moment, okay, because there's a lot of electrons over here, electrons and electrons, they repel. Okay, electrons and electron, they repel. What happens to this electron from this molecule? They tend to move more over here because they are being repelled by this delta negative. Okay, so making less electrons over here. And what happens over here? There is going to be delta negative and delta positive. And there will be some sort of interaction between this delta negative and delta positive. But take note, since it's camera, for that moment, okay, for that moment, if you take another picture, then the bond will be broken. You have another new bond. So this bond, okay, is not permanent. It's temporary. Okay, it's temporary. If it is temporary, okay, of course the bond is not strong. It's like a boy and girl, okay, they are in relationship, okay, but that relationship is going to be on and off, then on again, then off again. So of course that bond is not strong, okay. So it's a temporary relationship, okay, on and off, okay, the bond is not strong, okay. So of course the same thing when it comes to van der Waals forces of attraction. Okay, this is going to be not a very good forces of attraction, because if I take for next moment, maybe this bond is going to be broken, and then you will have the van der Waals forces in some other places. Okay, so this one is important, okay, to note. Okay, saying that this van der Waals forces is not permanent. Okay, it can change because of the movement of electrons, and do remember, van der Waals forces depends on electrons. It means that, okay, if you have more electrons, if you have more electrons here, it means this delta positive and delta negative will be much more greater. Okay, delta positive and delta negative, it means you have a lot of negative, a lot of positive. So of course they will be greater. So it is said that you will have a stronger van der Waals forces when you have more proton number. It means when you have more electron. So you will get more electron when generally when you have the size which is bigger. Okay, so if you go across, go down a particular group, for example, we know the size is getting bigger because number of shells are increasing. And because number of shells increasing, we know also electrons are also increasing. Okay, so if the electrons are increasing, I can say that, okay, as I go down, okay, my van der Waals forces will actually become bigger and bigger. Why? Because more electrons. Okay, this one will be something to do with van der Waals forces of attraction. Okay, is there any question on van der Waals forces? So do remember, van der Waals forces depends for it applies for all kind of molecules, but when it comes to non-polar molecules, okay, the only intermolecular forces that actually exist is going to be van der Waals forces only. Okay, therefore, okay, the non-polar molecules generally will have lower boiling point, okay, compared to polar molecules. Okay, why? Polar molecules, they will have permanent dipole-dipole, or better still, if they have hydrogen bonding, then their boiling point will be generally higher, okay, compared to the non-polar molecules. Okay, therefore, if you see chlorine, okay, if you compare chlorine with alcohol, okay, alcohol, even though the boiling point, ethanol, for example, 70 degrees Celsius, we know at room temperature chlorine, room temperature is going to be what, 27 or 28 at 27 degrees Celsius. Okay, we know that chlorine is going to be gas. Okay, so it means that at 27 they are already gas, but alcohol, okay, needs to reach 70 degrees Celsius to change into gas. Okay, so you can see over here why it requires a bit more energy. Okay, because alcohol has hydrogen bonding, but when it comes to Cl, in order to change their to gas, they only have van der Waals forces of attraction, something like that. Okay, I want you to actually remember. So the boiling point is generally lower compared to those other compounds or those other molecules that are going to have hydrogen bonding or permanent dipole-dipole bonding. Okay, so if let's say we want to summarize today's